Are there any questions? You got to come up with one? Trying to interpret your look, whether it's the, I know I had a question, what are the notes, or, let me just see if something strikes me. I guess more the second.
It was supposed to be the blank look, that means I have no question.
Okay. Okay, you just forget one more thing. All right, so compressibility deals with how easy is it to actually compress a material. Change its density, as it were. And K is the reciprocal of what is known as the bulk modulus. So we've talked about, I guess the equivalent would be other density. Oh, let's just, into, the analogy would be something we haven't covered, so I'm not gonna worry about it. The bulk modulus is defined as the ratio of the change in pressure on an object over the change in volume per volume. So if I increase the pressure on whatever the material happens to be, if I increase the pressure on the outside of this Pepsi container, how much will it actually shrink? And so the bulk modulus will be related to the change in the pressure that I apply and then the actual change in volume per meter volume. And then take the reciprocal of that to get the compressibility. So for steel, we have, make sure I'm getting the right thing there. Yeah, the bulk modulus for steel, 160 times 10 to the 9th. And then the SI units, since the denominator here has no units, because it's a volume over a volume, the units would be the units of pressure, which would be pascals or newtons per square meter. And the compressibility would just be the reciprocal of that, which, there we go, 6.25 times 10 to the negative 12. Inverse pascals, or meter squared per newton. So if I took a piece of steel and I plunged it 4,000 meters into the depths of the ocean, how much would the volume change? Well, I know that the change in volume per volume is going to be equal to the change in pressure over the bulk modulus. We've already talked about the pressure connected with depth. I'm pretty sure we did that last time. And so this is going to be the density of the water times G times the depth itself over the bulk modulus. And just simplifying some numbers here, this is 1,000 kilograms per cubic meter. I'll just make it 10 meters per second squared, and a depth of 4,000 meters, divided by 160 times 10 to the 9th pascals. And that gives us
times 10 to the negative 4.
So in essence, the volume of this block of steel would shrink by 0.025%. Not a huge amount. Water, since we're talking about fluids, we probably should talk about water. The compressibility of water. Since I'm probably going to stick with W for water, let's start it here. For water is 45.8 times 10 to the negative 11th meters squared per Newton. And so what would be the bulk modulus?
Got 2,183,000,000.
2,800,000,000.
34. Wait, no. 183 million. Etc. I don't want to read out all these digits.
So 2.18 times 10 to the 9th pascals is the bulk modulus. So if I had some block of water, so just imagine I get some cohesive block of water and I shoved it down to 4,000 meters below the surface of the ocean, it would be compressed by, well, we'll go through the same process, the only difference is the denominator there. So on top I've got 40 million, 4 times 10 to the, so 1, 2, 3, 4, 5, 6, 7, 4 times 10 to the 7th, divided by 2.18 times 10 to the 9th. So this would be delta V over V. I'm making some very simplifying assumptions here. One, the density of water, well, I'm gonna contradict myself. I assume the density of water surrounding that block is gonna remain constant. Okay.
Oh, it did turn on. Okay. It wasn't turning on this whole time. I don't know
It's best with your head.
I got 101832.
0.01822.
32.
32. All right, so 1.8%. So the water that my block of water that I stick 4,000 meters down below is the density is going to change by 1.8%. So when I talk about it, fluids being incompressible, this gives you some idea of the incompressibility, the fact that the density of water is going to change by 1.8% if we go 4,000 meters down below, so a couple miles below the surface of the ocean. Because a lot of what we're about to cover assumes fluids are incompressible. All right, last time I believe we did cover the pressure at a particular depth. So let's look at recognition. I was thinking that's what we did at the end of the class.
Last thing I wrote down was the buoyant force.
Was the what?
Buoyant force.
We would have done it before buoyant force. So I feel like shifting pressure at depth y from the fluid is equal to density of the fluid times G times y. And the buoyant force, the magnitude of the buoyant force, density of the fluid times the volume of the solid times G. So we've got rho GY and rho GV. So those we will exploit. Questions before I erase? All right, let's just take a simple example. I have a block of ice. That is sitting in water. How much of the block of ice is actually going to be sitting above or sitting below? Well, I know that the buoyant force is equal to what I have over here. This volume of the solid, this is the volume of the solid that is submerged. So we're only looking at this part of the ice and not this part of the ice up top. So, given the block of ice, I've got weight acting down, I got buoyant force acting up, and I apologize because I know how much you love doing force diagrams. So I get mg acting down, buoyant force acting up. I'm assuming it's an equilibrium, I just didn't throw the cube into it, it's sitting there. So FB is equal to mg. And so we have density of the liquid, water, times the volume of the cube, put a little s there for submerged, times G is equal to mass of the cube, which is just going to be the density of the ice, times the volume of the ice. Well, I made it a cube to make it easier. If each side is length L. I'm gonna make this distance here H. So we have the density of the liquid water times the volume of the cube, which is just gonna be the area of this surface area right here, which is L squared, because I made it a cube, times H, times G, is equal to the density of ice times the volume of the ice, which is L cubed. Cancel it out what we can. We get H is equal to density of ice times L over density of the liquid. And density of ice, I looked it up and I got 4 different values very quickly. They're all roughly in the same ballpark. Let's just go with 0.92 over 1 times L. In other words, 92% of the ice cube will be underwater. Thus the iceberg, 90% of an iceberg is hidden, kind of thing. All right, questions? Do it over here. I have a triple beam balance. And I put a block on it. The block has a mass of 79.4 grams. I now take that block and my triple beam balance, and I suspend it from underneath. What will the mass be now?
Still 79.4.
I hope so. Yeah, it should still be 79.4 grams. Now I take water, a container with water, and the cube, we'll make it a cube again, 3.1 by 3.1 by 3.1 centimeters. What will the balance say now? So, how do we start?
By creating a force diagram.
Oh, all right. What are the forces acting on?
Tension.
Force due to gravity.
Force due to buoyancy.
Acting which way?
Up.
Now, it's sitting there in equilibrium. If we actually want to come up with a legitimate mass here, it does need to be at rest and staying at rest. So we have FB plus FT minus RPW. Which one of these is going to be what the scale reads?
Would it be the combination of all of them?
No, I mean, this. Yes and no, but specifically, and I unfortunately called it a scale, it actually is a balance. One of these is directly impacting the balance. The others are peripheral, indirectly affecting it. Which one directly affects the balance?
The force due to gravity? No. The tension?
Yeah, it's the tension, the rope that's connected. So we're basically trying to figure out what that is. And then figure out what mass would cause that. All right, so let's start putting stuff in. Buoyant force, that is going to be equal to the density of the water times the volume of the cube times G plus the tension is equal to mg. So my tension is going to be mg minus the density of the liquid times the volume of the cube times G. So we have the mass of the cube itself, and then we have the mass of the water that is basically getting pushed out of the way. So I end up with 79.4 minus, let's do it this way, let's factor G out. So I get M minus rho L V C. So 79.4 minus 1 times whatever the mass, volume is that. Just wait somewhere between 27 and I'm guessing 30.
29.79.
So 79.4 minus 29.79 is
49.61.
and that's going to equal the tension. Now the balance is looking, it sort of takes the acceleration of gravity out of play because it's affecting both sides of the balance. And so that's gonna be equal to sort of the effective mass times G. And let's not confuse our G's. This G here is grams, this G right here is acceleration due to gravity. But the balance will now read 49.61 grams. Now the mass hasn't actually changed, it's just sort of an apparent mass. And for the next one, I'm gonna pause this, I'm gonna go grab some props that I meant to grab earlier. So we don't miss every exciting bit of action. Good thing I hit record before I did the shaking here. Good enough. All right, so we have the block that's now hanging down there. It's 85.2 grams. And so if we stick it in water, oh, that's right. I had the water here. I need something to prop underneath it. And this one will be good enough. Oh, so close. Now we definitely don't want it touching the bottom because then we introduce another force.